Okay everyone, welcome to the NUPOC video study guide number 70. I know it's been a couple weeks since the last video, but let's get right back into some of these physics problems and specifically dynamics. And in fact this problem is has some elements of electromagnetics in it, so hopefully it'll make a good segue into some of the electrical engineering and electromagnetics problems that we'll end up doing shortly. This problem basically presents us with some sort of computer screen or TV or something like that, where we have some screen up here, right? And then we have an electron, right? A charged electron, right? That's traveling with some initial velocity in this direction and is going to strike the screen right here at this midpoint. It's actually D. It defines the width of the tube here behind the screen as D. The width of that tube is D, and the height of the electron above this bottom plate is d over 2. So if nothing happens, this electron will just have some initial velocity and it will go ahead and just strike the tube at point D. D over 2 from the bottom plate here. But we have some voltage applied between these two grates, right? Between these two plates. We have a positive voltage here, and these plates are insulated from each other, so it's like a capacitor, right? There's just charge building up on the two plates, and so we have some positive charge building up on the top plate, and the bottom plate is just earth grounded, so it might not have a negative charge building up on it, but it will be negatively charged relative to, or it will have a lower charge than the top plate. So let's just say it has some negative charge there. And so we have an electric field between these two plates, and by convention the electric field vector will point from the positive charge to the negative charge, and so we have this electric field. So since we have this electron that's traveling through an electric field with some constant velocity, right? We have some, well, even if it wasn't traveling with some constant velocity, we have some electron, a charged electron, in an electric field. So this field is going to exert a force on the electron. And in fact, that's the Lorentz force, right? Which we'll see again in a lot of our electromagnetics, especially our like motors problems, and that sort of thing, where you have an electric motor or an electric generator, which basically says that the force on a charge, right, is just the value of the charge, right? This is an actual signed value, right? This is not charge magnitude, times the electric field plus the velocity of the charge, right, cross the magnetic field, right? Of course here we don't have any magnetic field, we don't have any B field, right? So this whole term is 0. But if we did have this term, this would be what's called like our motional EMF, or sometimes called the back EMF in motor problems, or in a generator. This is actually the internal voltage of the generator, right? In a generator, in an electric machine, the B field actually dominates the E field. But here this is more of like an electrostatics problem almost. So we don't have a B field, we just have an E field. So without this term here, right, F just equals QE. Okay? And we know that the charge on an electron is actually negative, so Q in this case would be a negative number. So F, right, the force, the vector of the force is actually acting in the opposite direction of the electric field, since Q is negative for an electron. So we could say, Q of an electron equals negative the magnitude of Q, and we can just say that Q is like the elemental charge, right? So an electron is minus Q, or minus the magnitude of Q, and say a proton would be plus the magnitude of Q. So let's just use the magnitude of Q. It's just simply the magnitude of the elemental charge, right? Okay, and we could even say it's minus the magnitude of QE, since the magnitude of an electron's charge is equal to the magnitude of a proton's charge. So we can just say this is QE equals minus the magnitude of QE. All right. So, anyways, we want to know where this electron strikes this screen, right? So we want to know how the path of the electron, if there was no electric field, it would just go straight. But now we know we have a force and it acts in the opposite direction of the electric field, so it acts in this direction, right? We have some force, right? And let's say that's force on an electron, so let's say it's F sub E, right? And so we know that the path is just like projectile motion, right? It's going to sort of be distorted up in this direction, right? Just like gravity distorts the path of a projectile. If you threw a baseball or something like that, it would be a parabola. And just a quick side note, we are neglecting gravity in this problem. So there would be a force of gravity pulling down on the electron. But in an electrostatics problem like this, if you have some high electric field, the force due to the electric field on the electron is going to far outweigh the force of gravity. So really we can safely neglect the force of gravity in this problem without really changing the problem at all, or without really changing the answer to the problem significantly. So if we have a force on the electron in this direction, that means we also have an acceleration on the electron in this direction, right? And so we can say that Fe, right, equals, we know that it equals minus the magnitude of QE, which is our Q in this case, right, times the electric field. Well, the electric field is just in terms of volts per meter, right, or volts per length, right? And so here we have a distance of d between the two plates, and we know that there's a potential difference of V, right, between the two plates. So the electric field is simply V over d, right, and it is in the minus y hat direction. Now we can also say F equals ma, right, so we can say Fe equals mass of the electron times acceleration of the electron, right, which I'll say the acceleration of the electron is just ae, and it's in the y hat direction. Now we can take this negative sign and cancel it with this negative sign, and so we can move the mass of the electron over to the other side of the equation here, and we can find out what the acceleration on the electron is. So we can say that ae, and I'm going to kind of put the ae and the y hat together and just call that our ae vector, right, which is in the y hat direction, equals the magnitude of the charge of the electron divided by the mass of the electron times the voltage between the two plates divided by the distance between the two plates, and it is in the y hat direction, right? So now, how does this get us any closer to finding out where we're going to strike this plate here? All right. Well, now we know what the acceleration is, and we know it's a projectile motion problem. So let's just go ahead and use our projectile motion equations from dynamics, right? So we know that y final, I'm going to say this is the final position of the electron. And by the way, I should have done this at the beginning of the problem, but we really should clearly define our coordinate system. I'm going to say this is x hat, this is y hat, and coming out at us is z hat, right? Which is pretty much the standard for most dynamics problems, right? So when I say AE is acting in the positive y hat direction, I mean it's acting in the upward direction from our perspective here. So y final, which is the final position of the final y position of the electron, equals, right, 1/2 the acceleration of the electron, right, times t squared plus v0y of the electron times t plus y0. Well, we have no initial velocity in the y direction, so this term is 0. This term y0 right here, we can just say that that's d over 2, right? That was the initial y position. If we say that this bottom plate here is y equals 0. And now we know what AE is, that's just right here. But how much time does it take for the electron to travel from its initial point here at, let's say, x equals 0 over here to x equals L, right? This is x equals 0, x equals L. Well, there's no acceleration in the x direction, so it has the same velocity from x equals 0 to x equals L, right? So the time it takes to get there, right? If L was bigger, it would take more time. If V0 was bigger, it would take less time. And we know that V0 is in terms of meters per second, L is in meters. So we know that the time it takes to travel from x equals 0 to x equals L, or from the initial position to the screen, is simply going to be L over V0, right? Or the magnitude of V0. Okay? So YF then equals 1/2 A, which is QE V times, I'm just going to bring in the t squared now, so t squared equals L squared over V0 squared, so this is L squared over mass of the electron times D times V0 magnitude squared, right? Plus D over 2, right? So this is the position, the y position that the electron will strike the screen at. And so we can say then that as long as this term right here is less than d over 2, the electron will hit the screen, right? Or if the polarity was reversed, we would say that it would really be the same thing. We would just have an opposite polarity and the electron would move in this direction. So as long as this term is less than d over 2, then the final y position will be less than d and the electron will strike the screen. If this term, the magnitude of this term is greater than d over 2, then the electron will end up striking one of these plates, right? So that kind of answers this question of whether or not the electron even strikes the screen. And then we can say, what can we change, right, in order to adjust the position where this electron strikes the screen, right? Well, if L and D are fixed, if the geometry is fixed, then really what we can change is the voltage between the two plates here, right? And we can also change the initial velocity of the electron. So if the electron is moving faster, right, then it will cover less distance in the y direction by the time it hits the screen. And if the voltage between the two plates is higher, then it will get pulled more towards the plate, more strongly towards the plate as it travels in that direction. So a higher voltage moves the electron towards the edge, and a faster initial velocity moves the electron more towards the center of the screen.